हरि करना।
So far we have seen some of the terms of statistic. So now we will look into the most important theorem. It's central limit theorem. So central limit theorem states that if given a sufficiently large amount of sample size from a population with a finite level of variance in any distribution, assuming that all samples are identical in size, the mean of all samples from the same population will approximately equal to the mean of the population, and the distribution will tend to become a normal distribution. That's what is a central limit theorem. So let's take this example. Let's x1, x2, x3, and so on, xn plus be a sequence of independent and identically distributed random variables with means mu and a variance sigma square. And let x is equals to x1 plus x2 plus x3 plus and so on xn. So then as n increases, the distribution of x, fx of x converges to the normal distribution. So that's what a central limit theorem says, and that's what you can see on the screen. So when n increases, the distribution will become more and more and more normal. See that? The spread of distributions will decrease. See that? From here, we reached here. So let's take a small example. If a dice is rolled, the probability of, let's take this example and note down here. So it's a central limit theorem. Yep. So now let's take this example. If a dice is rolled, one dice, the probability of rolling one dice is, so let me put that, the probability rolling one dice, a probability of rolling one dice, a probability of rolling a one from one dice, that would be much easier, much better way to put. The probability of rolling one, that's number one, from one dice is P is equal to 1 divided by 6, correct? And a 2, again, to roll a 2, again, P is equals to 1 divided by 6. And 3, 1 divided by 6. 4, 1 divided by 6. 5, 6, also 1 divided by 6. The probability of the die landing on any one side is equal to the probability of landing on any other 5 sides. Suppose if there are about 1000 students in a school and each of them is made to roll the same dice, then the collection of random variables generated from the above experiment will be sufficiently large enough on the histogram. Then it will tend to become a normal distribution. Okay, now let me show here. See, this is one dice was rolled. You got 1, 2, 3, 4, 5, 6. This is by and large equally distributed. This is uniformly distributed. Then you got the 2 dice rolled out and then we mapped it. This is what we got. But as the number of dice are increasing, or you can say number of dice are increasing, then it's getting closer to the normal distribution. That's what is normal distribution. So now let's take more concrete example. Okay. So just I'll get back to this example, the previous example. So here we have mapped the income. Whatever you're seeing, that's the population income. Then if you see this the first graph is the data distribution. So whoever the individuals who have provided the income, so their distribution, this is what the shape we got. Then we have taken a samples, not one, many samples. Total, it's a huge data, 10,000 data points it has. Out of the 10,000 data points, we have taken some samples, and each sample size is 5. And then we have calculated the mean of each sample, and then each sample mean frequency has been calculated later, and then we plotted on the distribution, and this is what we got it. So that is the difference between a data distribution and then sampling distribution. This graph is known as the sampling distribution from here to here, because here we calculate the frequency of the sampling statistic, where in data distribution we calculate the frequency of the data point occurrence or category occurrence. If you remember, we have dealt with data distribution in organizing data in descriptive statistics. And when it comes to here, this is sampling distribution. Here we measure the mean of the sample, that is known as the sample statistic. Now the frequency of that sample statistic occurrence will be plotted on the graph, that is called a sampling distribution. So when the mean, if your sample size is 5, this is what the shape. If the sample size is 20, it is becoming more normal, and then the spread is also reduced. And simple terms, this is what we call it as a central limit theorem. Let's look into the one of the simulation of it. Let's do that. Yep. So this is the central limit theorem, and this is what the code is written for that. Okay, and this is what the picture you can see. So if you see the overall, you got the 10,000. This is what is our population. So now it was made into 1,000 samples. Okay, total number of samples would be 1,000. Then initially I have started with sample size 1. Let's see. This is what we got. There is a lot of if you see that this is what the normal curve, and there are a lot of breaks in the overall curve. It is not exactly fitting with the normal curve. So now I'll bring it to 10, sample size 10. Let's see. Now you see that it has been improved as I have increased the sample size. It's approximating to the normal curve. You see that this is our normal curve, and it is approximating to the normal curve. Now let me increase it to the 20 and see the magic. Now you see that it's this side, it's pretty, it most of thing was captured. It's fitting well now. It's fitting well, neither under fitting nor over fitting. It's trying to fit well. Let me bring it to the 40 and see what's going to happen. See that this portion was completely, by and large, almost fitted. Here we have some gap, here some gap, here some gap, but this portion was fitted. There is a huge gap here. Now let me bring it to the 60. I'm increasing my sample size, this side it fitted well, and this side it's gone. You see that here it's gone, but one side it's approximating, it's closing, it's inching towards the normal curve. Let me make it to 80. Yeah, and the bottom portion was exactly fitted. You see that the bottom portion, the bottom portion was fitted well. Now let me make it to the 100. These many only we can make it, and here is the shape which is exactly fitting well. Here even at the top it's taking up. Here it's fitting well. So from 1 to 100, the sample size has been increased, and it slowly took up the shape of the normal curve. This is what we call it as a central limit theorem. If you want, you can copy the code from here. These two are NumPy and Matplotlib. After that, you can see. Yeah, take a snapshot and copy the code for the simulation. So now let's look into the simulation with this one. So here they have mentioned uniform, skewed left, skewed right, normal. These are all different distributions that are available. Now I will begin with the uniform distribution. So this is our uniform distribution. Now you can click to the sample size and draw the sampling distribution. If you click on any, so based on that sample size, they will create a sampling distribution. Let me click on n equals to 2, and you can clearly see the uniform distribution. This is population. This is called a data distribution. Our data, whatever data that population has, the data distribution is in uniform shape. You see that? And then mean of this data, population parameter is 200, and standard deviation of the population is 115.47. Now let's try to draw sampling distribution varying with various sample size. We will begin with a sample size of n is equals to 2, and this is what the shape we got. So total number of samples they have used is 20,000, and then mean of this is 200.74, and standard deviation is 81.85. So this is a simulation of randomly selecting thousands of samples from a chosen distribution. The purpose of this simulation is to explore the central limit theorem. You will learn how the population mean and standard deviation are related to the mean and standard deviation of the sampling distribution. So here you can see the x bar, that means these are called statistic. Okay, these are not parameter, these are belongs to samples. So first you will be asked to choose a uniform or skewed, whichever, and then you have to select the respective one. So then you will able to see. That's what the process here. Okay, anyway, we have selected the sample size. This is what the shape we got. Now let me increase the sample size to 9. Oh, it's pretty better. And 25, you got the nice distribution, but still there are some deviations. This is brilliant. 36, let me bring it to the 100. This is nice. You see that you got the random, you got the normal distribution curve, and then the spread has been reduced. The spread has been reduced. You see that spread has been reduced. And this is, let me come to the 25. You got when it is 25, you got your shape exactly. No, the standard deviation is, there is a huge difference, but the mean of the mean statistic is same as mean parameter, close, by and large close. But anyway, one thing we can prove with that, as the sample size increases, it will, our sampling distribution will be inching towards the normal distribution curve. Let me take one more distribution, this time skewed left. You see that? Completely skewed left. The left side has been skewed. You see that? Now, n is equals to 2, obviously skewed left. N is equals to 9, slightly better. N is equals to 25, you should see that normal distribution curve. 36, spread is reduced. 100, spread is completely reduced. Okay, now let's get into the third one, that's skewed right. You see that the right portion of your graph has been skewed. So begin with n is equals to 2, skewed right, 9 normal, 25 better, 36 reduced spread, perfect spread. Now let's get into the normal distribution curve. Even let's imagine even your data, your population data itself normally distributed. Always you should make a distinction between data distribution and sampling distribution. Always make that distinction. Whatever you are seeing here is a data distribution of the population. So here we will be, so if the sample size is 2, this is the sampling distribution that we are getting. And 9, the spread is reduced. 25, the spread is reduced very much down, but the you see that it took a proper normal distribution curve. That is x, spread is reduced further down, 100 completely reduced. That's what is our central limit theorem. So the phenomena